Many scientists say the probability of alien life in our galaxy is high. This is simply not true. Let us explore exactly why that is, and why the Fermi paradox has an easy solution. Our galaxy, the Milky Way, is home to hundreds of billions of stars. And beyond our galaxy, there are hundreds of billions of other galaxies, each with its own blizzard of stars. The numbers are staggering, and this is the only reason why you've been made to believe that there must be life out there. But this has no scientific basis. Yes, this vastness naturally leads us to ask a question that has echoed through human history, whispered by philosophers, scientists, and anyone who has ever gazed at the stars in wonder. Are we alone? Out of all those worlds across all that space, is Earth the only planet where life has awakened and developed intelligence? It feels almost impossible, doesn't it? With so many potential homes for life, surely someone else is out there looking up at their own sky and asking the very same question. It is a profound thought, one that challenges our place in the cosmos. The search for extraterrestrial intelligence, or SETI, has been going on for decades. We have built enormous radio telescopes, giant electronic ears pointed at the heavens, listening for a signal, a whisper, a sign that we are not the only thinking beings in this cosmic drama. We scan the skies, hoping to intercept a message from a distant civilization. So far, the universe has been silent. The great cosmic silence is both puzzling and a little bit unsettling. Why haven't we heard anything? The lack of evidence forces us to reconsider our assumptions and look closer at the conditions needed for life. Perhaps the answer lies not in the number of planets, but in the nature of the stars they orbit. When we imagine other worlds, we often picture them orbiting a star like our own sun, a stable yellow G-type star. But our sun is not the most common type of star in the galaxy, not by a long shot. To understand the chances for life, we must first understand the true nature of our galactic neighborhood. We need to embark on a journey, not just through space, but through the science of stars themselves, to see what kind of homes the universe truly offers. When we picture a star, we usually think of something like our sun, bright, yellow, and a source of steady, life-giving warmth. It sits at the center of our solar system like a benevolent cosmic parent, nurturing the planets in its care. The sun has been remarkably stable for billions of years, allowing life on Earth the time it needed to evolve from single cells into the complex web of creatures we see today. But this picture, while true for us, is not representative of the galaxy as a whole. Our sun is, in a cosmic sense, a statistical minority. It's a bit of an outlier. The most common type of star in the Milky Way is something entirely different. They are called red dwarfs. These stars are much smaller, much cooler, and much dimmer than our sun. Imagine a campfire instead of a bonfire. If our sun is a bright halogen lamp, a red dwarf is more like a dim, red nightlight. They are so faint that you cannot see a single one in the night sky with your naked eye, despite them being the most numerous stars all around us. About 3/4 or 75% of all the stars in our galaxy are red dwarfs. They are the silent majority of the cosmos. Because red dwarfs are so much cooler than our sun, a planet would have to orbit much, much closer to one to stay warm enough for liquid water. Liquid water is what we believe to be a key ingredient for life as we know it. If a planet orbited a red dwarf at the same distance that Earth orbits the sun, it would be a frozen, desolate ice ball. To get into the habitable zone, the region where temperatures are just right, a planet would need to huddle incredibly close to its tiny red parent star. This proximity, this closeness, creates a whole new set of problems. This simple fact changes the entire game when we talk about looking for life. If most stars are red dwarfs, then most of the planets in the galaxy are orbiting red dwarfs. This means that the most common type of planetary system in the universe is fundamentally different from our own. We can't just assume that what happened here on Earth can easily happen everywhere else. We have to look at the specific conditions around these dim, red suns and ask a difficult question. Are these places truly suitable for life to begin, and more importantly, to thrive and become intelligent? Huddling close to a star for warmth might sound cozy, but for a planet orbiting a red dwarf, it's a position of extreme danger. While these stars are small and dim, They are also incredibly violent, especially in their youth. Red dwarfs are known for being flare stars. This means they can suddenly and unpredictably erupt in powerful flares of radiation. These flares are like gigantic solar storms, but they can be hundreds or even thousands of times more powerful than any flare ever recorded from our own sun. They are outbursts of monumental energy and fury. A planet orbiting in the habitable zone of a red dwarf would be blasted by these flares at point-blank range. Imagine standing next to a campfire that, without warning, explodes into a towering inferno. This is the reality for a habitable world around a red dwarf. These flares would unleash a torrent of high-energy X-rays and charged particles. Such intense radiation is incredibly destructive to life as we know it. It can strip away a planet's atmosphere over time, leaving the surface exposed to the harshness of space. It can also sterilize the surface, killing off any simple life forms that might be trying to get a foothold. Furthermore, planets orbiting this close to their star are likely to become tidally locked. This is the same phenomenon that keeps one side of our moon always facing the Earth. A tidally locked planet would have one side in permanent daylight, constantly baked by the star, and the other side in permanent darkness, frozen in an endless night. This would create extreme temperature differences between the two hemispheres. A sliver of twilight zone between the hot and cold sides might be habitable, but it would be a very narrow and precarious place for life to exist. So, the very thing a planet needs to do to stay warm, orbit closely, puts it directly in the line of fire. It's a cosmic catch-22. To have liquid water, you must endure these catastrophic stellar tantrums. You must survive having your atmosphere slowly sandblasted away into space. You must cope with being tidally locked, with one side of your world scorched and the other frozen solid. These are not friendly conditions. They paint a picture of a planetary environment that is hostile, unstable, and profoundly challenging for the emergence and survival of life. Let's imagine for a moment that life somehow manages to get started on a planet around a red dwarf. Despite the violent flares and harsh radiation, what would that life be like? It would have to be incredibly resilient. Perhaps life could exist deep underground or in the oceans, where it would be shielded from the worst of the star's radiation. Simple single-celled organisms like bacteria might be able to survive in such a protected environment. They could hide from the stellar storms, waiting for the fury to pass, before venturing out again. This is a plausible scenario for microbial life. But we are not just talking about any life. We are talking about intelligent life. Intelligence, as we understand it, requires a complex organism. It needs a nervous system, a brain and sensory organs to perceive and interact with the world. Building such a complex creature takes a very long time, billions of years of stable, continuous evolution. On Earth, it took nearly 4 billion years to go from the first simple cells to creatures that could build telescopes and ponder the stars. A stable environment was the key ingredient that allowed this long, unbroken chain of evolution to unfold. The constant, violent interruptions on a red dwarf planet would make this kind of steady progress incredibly difficult. Every massive flare would be a potential extinction event, a great filter that could wipe the slate clean. It would be like trying to build a complex sandcastle while the tide keeps coming in and washing it away. Even if life re-emerged after each catastrophe, it might never get the chance to evolve beyond the simplest forms. The evolutionary clock would be constantly reset. The long, quiet eons needed for complexity and intelligence to arise might simply never happen. This is a crucial point. The path to intelligence is not just about having the right ingredients like water and organic molecules. It's also about having the right conditions over immense stretches of time. It requires a cosmic parent star that is gentle, stable, and predictable. Our sun provided that for Earth. But the vast majority of stars in our galaxy, the red dwarfs, are anything but gentle. They are temperamental and violent hosts. The most common real estate in the galaxy might just be the most dangerous, making the leap from simple microbes to thinking, tool-using beings a near impossibility. There is another, even more fundamental problem we face when we think about alien life. It's a question so basic that we sometimes, forget to ask it: what exactly is life? And how does it start? Here on Earth, we can see life all around us. We can study it, sequence its DNA, and observe its incredible diversity. But really, we are looking at just a single data point. All life on Earth shares a common ancestor and a common biochemistry. It's all based on carbon, uses water as a solvent, and stores its genetic information in DNA. But is this the only way? The truth is, scientists do not know how life first began. This process, called abiogenesis, is one of the biggest unsolved mysteries in science. We have some ideas, of course. We think that in the primordial soup of early Earth, simple chemical compounds, energized by lightning or underwater volcanic vents, somehow organized themselves into the first self-replicating molecules. These molecules were the humble predecessors of life, but the exact steps, the precise sequence of events that turned non-living chemistry into living biology, remain shrouded in mystery. We are trying to find something without knowing how it's made. It's like searching for a car in the universe without knowing what an engine is or how it works. We assume alien life might be like us, based on carbon and water, because that's what worked here. This is why we look for Earth-like planets in the habitable zones of stars. But this could be a profound failure of imagination. Could life be based on silicon instead of carbon? Could it use methane instead of water? Could it exist in forms so strange we wouldn't even recognize them as being alive? This uncertainty makes our search incredibly difficult. If we don't know the recipe for life, we don't really know what ingredients to look for. And if we don't know what life looks like, we might be staring right at it and not even realize it. The silence from the cosmos might not be because no one is out there. It could be because we are looking for the wrong thing, in the wrong places, with the wrong tools. The problem isn't just that the universe is vast, it's that our own understanding of life's fundamental nature is still so very limited. Our search for extraterrestrial life is profoundly shaped by our own existence. We are the only example of an intelligent, technological species we know of, so we naturally look for others like us. We listen for radio signals because that is a technology we developed and understand. We imagine aliens building spaceships and cities because that is what we do. We are, in a sense, searching for a reflection of ourselves in the cosmic mirror. This is a reasonable starting point, but it's also a very narrow one. It makes a huge assumption that the path of evolution everywhere else will lead to the same destination it did here. Think about the sheer randomness of evolution on our own planet. If you could rewind the tape of life on Earth and play it again, would humans evolve a second time? Many biologists think the answer is no. The evolution of intelligence was not an inevitable outcome. It was the result of a long series of cosmic and biological accidents, a lucky asteroid impact that wiped out the dinosaurs, allowing mammals to thrive, a specific series of climate changes in Africa that favored primates who could walk upright and use tools. 1,000 other chance events had to fall into place. For every one species that developed high intelligence, there are millions, perhaps billions of other species that did not. Look at the incredible success of insects or sharks or crocodiles. These creatures have been around for hundreds of millions of years. They are perfectly adapted to their environments. They have survived multiple mass extinctions, but they have never built a radio telescope. From a purely biological standpoint, high intelligence is not necessarily a winning strategy. It's an energy-expensive, highly specialized trait that has appeared only once in 4 billion years of life on Earth. So even if life is common in the universe, even if countless planets around red dwarfs have oceans teeming with alien microbes, it doesn't mean that any of them will produce intelligent beings. The leap from life to intelligent life might be the greatest barrier of all. The universe could be filled with life, but it might be overwhelmingly simple, microbial, and non-communicative. The galaxy might be a lush garden, but a silent one, with no one to talk to. Our expectation of finding other thinkers might be the rarest outcome of all. Let's assemble the pieces of our cosmic puzzle. We start with a galaxy of hundreds of billions of stars. That sounds promising. But then we learn that most of these stars are red dwarfs, which are violent and hostile to life. This drastically reduces the number of stable, friendly environments. Of the few planets that might exist in safer conditions, only a fraction will have the right ingredients. the right size, a protective atmosphere, and the presence of liquid water. We are already winnowing down the possibilities from billions to a much smaller number. On top of these astronomical filters, we must add the biological ones. On a suitable planet, life must actually begin. As we've discussed, we have no idea how hard or easy that step is. It might be a near miracle that only happened once. But let's be generous and assume it's not that hard. Let's assume life starts on many of these perfect worlds. This life must then survive for billions of years. It must endure asteroid impacts, planetary climate shifts, and the slow aging of its own star. It must avoid all the cosmic pitfalls that could lead to its extinction. Then comes the biggest hurdle of all, the evolution of intelligence. As we saw, this appears to be an incredibly rare event, even under the ideal conditions of Earth. The vast majority of life will likely remain simple. The path to a complex brain, to consciousness, to the ability to question one's own existence, is not a guaranteed outcome of evolution. It may be a spectacular fluke, a 1 in a billion long shot that requires a specific, unrepeatable chain of environmental pressures and genetic luck. The galaxy could be full of worlds with life, but worlds with intelligent life could be exceptionally rare. And even then, we are not done. The solution to the Fermi paradox is that there is no paradox to begin with. The Fermi paradox wasn't based on any real data. We are not seeing anyone because there is no one out there to see. The universe is 13.8 billion years old. A technological civilization might only last for a few thousand years, or a few million at best before it succumbs to war, environmental collapse, or some other self-inflicted catastrophe. The window in time for two civilizations to overlap could be infinitesimally small. It's like two fireflies blinking once in a forest on a single night. The chances of them seeing each other are vanishingly slim. When you combine all these challenges, the odds of finding another intelligent civilization in our galaxy start to look incredibly long. This idea is sometimes called the Great Filter. It's a hypothesis that suggests there is some step in the long chain of events from a dead planet to a star-faring civilization that is so improbable that it acts as a barrier. Almost no life ever makes it past this filter. The question is, where is the filter? Is it the initial spark of life? The leap to complex cells? The evolution of intelligence? Or is it a filter that is still ahead of us? The challenge of surviving our own technology? Let's try a very rough back-of-the-envelope calculation, just to see how the numbers stack up. Start with 400 billion stars in our galaxy. Let's be optimistic and say 20% have planets in the habitable zone. That's 80 billion. Now, let's say only 1 in 100 of those are actually stable and suitable, not orbiting a violent red dwarf. We're down to 800 million planets. Now for the biological steps. What are the odds that life begins? Let's say 1 in 1,000. Now we have 800,000 life-bearing planets. What are the odds life evolves intelligence? Let's be very generous and say 1 in a million. We are now left with less than 1, 0.8 to be exact. This simple and probably overly optimistic calculation shows how quickly the monumental number of stars gets whittled down to almost nothing. The true odds could be far, far worse. The chance of life starting might be 1 in a billion. The chance of intelligence evolving might be 1 in a billion. If you multiply these low probabilities together, you quickly arrive at numbers that suggest Earth could be the only planet with intelligent life in the entire Milky Way galaxy, or even in our entire local group of galaxies. 1 trillion to 1 might not be a scientific certainty, but it captures the spirit of the immense unlikelihood we are facing. This isn't meant to be a pessimistic conclusion. It's a realistic one based on what we currently know about astronomy and biology. The universe is not obligated to be filled with beings like us. The silence we hear from the cosmos might be the norm. It might be the sound of a universe going about its business, a universe where life is a precious chemical reaction, but intelligence is an almost unrepeatable miracle. The absence of evidence in this case might just be evidence of absence. We may truly be on our own. So where does this leave us? It leaves us here, on this world, a small, fragile planet orbiting a stable, friendly star. It suggests that what we have here might be extraordinarily rare. The Earth is not just another rock. It is a world that won the cosmic lottery, perhaps 1 trillion times over. For billions of years, it has been a sanctuary, a place where life could take hold, evolve, and diversify in relative peace. It provided the long, unbroken stretch of time necessary for the slow, meandering path of evolution to eventually produce a species that could look back at the universe and appreciate its own improbable existence. This perspective changes how we should view our home. If planets with intelligent life are a dime a dozen, then our own existence is less significant. But if we are 1 trillion to 1 shot, then the Earth becomes something indescribably precious. It is the only known outpost of consciousness in a vast, silent cosmos. The thoughts we think, the art we create, the science we discover, these might be the only such things happening in our entire galaxy. This planet, this pale blue dot, is the sole guardian of a legacy 4 billion years in the making. This realization carries with it a profound responsibility. It is up to us to protect this planet and the astonishing gift of life it carries. We are the custodians of the only intelligence we know for sure exists. To squander that gift through conflict, neglect, or carelessness would be a cosmic tragedy of unimaginable proportions. It would be like extinguishing the only candle in an infinite darkness. The challenges we face, climate change, loss of biodiversity, the threat of nuclear war, are not just political or economic problems. They are threats to the universe's only known pocket of self-awareness. So, continue to look up at the stars. Continue to wonder and to search. The quest for knowledge is one of the noblest things our species can do. But as you look out into the vast emptiness, also look back at our own world. See it for the miracle it is. Understand that in a universe of staggering odds and violent realities, we are the beneficiaries of an almost impossible stroke of luck. We are the universe's way of knowing itself. And that makes our home and our lives infinitely precious. We are perhaps the lone voice in the cosmic choir. Let's make sure our song is one worth singing.